Today, I'm going to talking about the motion in accelerated frames, and you have to use your imagination in this class. So, let's begin. And we use to describe the motion of an object in an inertial frame. Now, we have to learn the physics in a non-inertial frame of reference. That is, one that is accelerating. For example, imagine there is a bus and a ball on the bus. And also there is an observer on the bus, and they are with a constant velocity, v. And the bus moving at a constant velocity. V represents it is an inertial frame. And observer on the bus seeing the balls at rest remain at rest, right? And Newton's first law appeared to abate. Okay, there is a consequence. Appear to abate because the ball is raised all the time. And however, imagine there is another bus and it has a acceleration. We could say that acceleration is non-zero. Okay. The acceleration bus is not an inertial frame. According to you, as an observer on the train, there appears to be no force on the ball. Yet however, it accelerates from rest toward the back of the bus, appearing to violate the Newton's first law. Okay, here is the thing. The ball will move back toward the back of the bus, and you are the observer on the bus. As a result, you observe the ball move toward the back of the bus, and it is obviously violates the Newton's first law. And this property is a general property of observation made in non-inertial frames. As a result, I will general of observation made in Okay, and I think the ball will move toward the back of the bus is a general property of observation made in non-inertial frame. There appear to be unexplained acceleration of objects. They are not fastened to the frame. Okay. On the accelerating bus, as you watch the ball accelerating toward the back of the bus, you might conclude based on your belief in Newton's second law that a force has acted on the ball to cause it to accelerate. We call an apparent force such as this one a fictitious force because it's not a real force and is due only to observation made in an accelerated reference frame. And this is a fictitious force. And after we define the fictitious force, there comes a question: how to identify the real force and the fictitious force? It's really simple because real force are always interaction between two objects. However, you cannot identify a single object for a fictitious force. Okay, and this is the answer. We'll write down. Real force are with interactions between two As we know, the uniform circular motion with speed v always has the acceleration toward the center. As a result, as we know, if we apply a force on an object, it will cause the change of its velocity, and it can be shown in two ways: is the change of its magnitude of velocity and its direction of velocity. So there is also a fictitious force in the case that act in the direction opposite that of the acceleration of non-inertial frame. Okay. Let us address this phenomenon in terms of Newton's law. Before the car enters the ramp, the passenger is moving in a straight line path. This is the straight line path. As the car enters the ramp and travels a curved path, the passenger tends to move along the original straight line path, which is in accordance with Newton's first law. The natural tendency of an object is to continue moving in a straight line. If a sufficient large force and act on the passenger as in this figure. This is a sufficiently large stall. However, the driver moves in a curved path along with the car. This force is a force of friction between her and the car seat. If this friction force is not large enough, the seat follows a curved path while the passenger tends to continue in the straight line path of the car before the car begins the turn. Therefore, from the point of view of the observer in the car, the passenger leans or slides to the right relative to the seat. Another interesting friction force is the Coriolis force large enough to enable her force caused by changing the radial position of an object in the rotation coordinate system. For example, suppose you and your friend are on opposite sides of the rotation circular platform, and you decide to throw a baseball to your friend. And according to this observer, who is in an inertial frame, the ball follows a straight line as it must according to the Newton's first law. At t equal to 0, you throw the ball toward your friend, but by the time tf, when the ball has crossed the platform, your friend has moved to a new position and can catch the ball. Now, however, consider the situation from your friend's viewpoint. Your friend is in a non-inertial reference frame because he is undergoing a centripetal acceleration relative to the inertial frames of the Earth's surface. He starts off seeing the baseball coming toward him, but as cross the platform, it veers to one side. Therefore, your friend on the rotation platform states that the ball does not obey Newton's first law, and claims that the side-away force is causing the ball to follow a curved path. This fictitious force is called the Coriolis force.
Examples where people build rotating reference frames using huge metal beams with seats mounted on the end, and it's all spinning on a bearing, and it might even be powered by an electric motor. But I've actually got two small kids, and we spend a ton of time here at this park, and this is one of the best rotating reference frames that I'm able to find. It's just your classic toy, a children's merry-go-round.
So to get a better view of the merry-go-round, we flew a drone above the playground and recorded as we set up the scene. So let's consider two participants/observers in this scenario. So one of them is standing on the non-rotating ground. Let's call this the reference frame. So to help us remember that this is the reference frame, let's name this observer Randall. R for Randall and R for reference frame. So the white pipes there are used to represent Randall's X and Y axis. And I know it might be a little bit hard to see, but these cards that are being placed on the ground are used to label this as Randall's point of view. And now you see that we're placing a camera here, which is attached to this non-rotating reference frame, and we're going to use it to gather Randall's point of view. Now the second observer is one that's attached to the merry-go-round. This is typically referred to as the body frame, and to help us remember that this is the body frame, let's name this observer Brian. B for Brian and B for body frame. So the gray pipes now represent Brian's X and Y axes, and again, we're trying to label this here with white cards that notify us that this is Brian's reference frame on the merry-go-round. And again, what we want to do here is set up another camera, which is now attached to the rotating reference frame and is going to be used to gather Brian's point of view. So you see, we're placing that camera right there. This is the one that's going to be a little bit interesting because we're going to see what they see. And this is basically the setup we have. So we've got the non-rotating reference frame down there in the bottom left as the white pipes. And again, that observer down there, we're calling him Randall. And then attached to the merry-go-round, we have another reference frame called the body frame, or Brian. And we're going to gather viewpoints from both of these perspectives as we move forward. So let's jump over and see a couple of interesting scenarios from both of these points of view. Let's start with a simple situation where nothing is rotating. If Brian and Randall are playing a simple game of catch and throwing this ball back and forth, nothing odd happens, right? The ball travels as you would expect. Now, let's watch this again, and we'll also slow it down. Now, let's add the drone's overhead view of the scene. Throughout the rest of the video, we're going to use these red transparent arrows to show the ball's trajectory. So again, this should look totally normal to you, right? If we examine the trajectory in the XY plane, as soon as the ball leaves the thrower's hand, it follows a perfectly straight line. Now let's start the body frame rotating. In other words, let's start spinning Brian. Again, we'll get the drone's overhead perspective but leave it stationary. Therefore, both the main camera and the overhead camera are effectively Randall's non-rotating point of view. And again, everything's normal. As soon as the ball leaves Brian's hand, it follows a straight line as you would expect. So everything seemed normal from Randall's point of view, but how about from Brian's point of view as he sits on the body frame? So to get an overhead view of what an observer in the body frame sees, we're going to use the drone again. So you can see the drone in this shot as the white quad rotor in the center. So we're going to position it directly above the merry-go-round, and as the merry-go-round starts spinning, we'll match the yaw rate of the aircraft with the merry-go-round. We could have achieved the same result by using a super tall tripod or ladder attached to the merry-go-round, but using a drone seemed much easier, cheaper, and more fun overall. So you can see that the overall end effect is that we have a camera that rotates with the body frame positioned about 20 feet above Brian's head. Now, let's look at that same scenario but from Brian's perspective. So in other words, we'll use the footage from the drone that's rotating at the same rate as the merry-go-round. Before we get started, I just want to point out a minor fact. In the first scenario where the merry-go-round was rotating and Brian was throwing balls, I accidentally spun it in the wrong direction. In this current video and all the subsequent videos, we'll rotate the merry-go-round in a counterclockwise direction for consistency. Let's look at Brian's point of view using the camera that's sitting on the merry-go-round, aka mounted to the body frame. Let's also start the drone rotating to match the yaw rate of the merry-go-round. Now this is odd. If Brian watches the ball as it leaves his hand, it appears to deflect to the right. To get a better view of this, let's slow this down to 30% of real time. Again, watch as the ball leaves Brian's hand. To an observer who's sitting on this rotating body frame, it appears that some mysterious force is accelerating the ball to the right. You can see that from Brian's point of view, the ball seems to follow this quasi-parabolic trajectory to the right. We know from the previous video that Randall, who's sitting on the non-rotating reference frame, just sees the ball fly in a straight trajectory as soon as it leaves Brian's hand. We'll throw it one more time so you can see this phenomena again. Remember that both of these videos are synced up and showing Brian's point of view, aka the viewpoint of an observer sitting on the body frame. This is definitely some interesting behavior, but we see that it's really just a matter of perspective. Randall sees one set of behavior because he's sitting on the non-rotating reference frame, and Brian sees something completely different because he's sitting on the rotating body frame. In the previous scenario, we tried to make it so the ball left Brian's hand near the center of the merry-go-round. In other words, we wanted to start the trajectory from the origin of the body frame. Once again, let's slow down the video, but only to 50% of full speed this time. Now, let's examine what happens when we release the ball from the edge of the merry-go-round. Let's rename this person as Edward. E for Edward and E for Edge. Edward is throwing the ball in four directions: radially outward, tangentially in the direction of travel, and radially inward here. And you can see that in all these cases, the ball is deflected to the right. Lastly, he's going to turn 90 degrees and throw tangentially in the direction opposite of motion, and the ball still deflects to the right. So regardless of location and direction, it seems that the trajectory of the ball is always deflected to the right when the body frame, aka the merry-go-round, is rotating in a counterclockwise direction. There does seem to be one scenario where things seem to act normally. We see that if Brian stands in the center of the merry-go-round and throws the ball straight up, everything seems fine. The main camera shows the point of view of an observer on the reference frame, and the picture-in-picture is an observer on the rotating body frame. In both cases, the ball rises and falls quote-unquote normally. Again, just keep this situation in mind, and we'll take a look at why this occurs when we do a rigorous analysis of the situation in the following video. The previous situations where we saw the trajectory being deflected depending on the perspective of the observer is called the Coriolis effect, and it has a lot of real-world scenarios. Speaking of real world, if you think about it, we're sitting on one giant merry-go-round right now called the Earth, and it rotates in this direction. So if we look at the northern hemisphere, this is very similar to the merry-go-round we were investigating where it spins in a counterclockwise direction. Now, let's consider what might happen if a low-pressure zone formed over the Atlantic Ocean. Now, let's consider the path of 3 air molecules. So initially, these are going to get pulled inward toward the low-pressure zone. We can then look at how the trajectory of these molecules move from the perspective of someone attached to the rotating Earth. So let's jump back to the merry-go-round and make a simulation of this scenario.
Okay, so now let's see if we can simulate the Coriolis effect from a meteorological perspective. So I've got an example here. This is my cardboard cutout of the United States here. And let's stick this on the merry-go-round up in what we're going to be using the merry-go-round to simulate the northern hemisphere of the world here. And then I've also got my horrible artistic cardboard cutout rendition of Europe here. So we'll put that on the other side and see if we can put an Atlantic Ocean in between. And we'll have balls going into the Atlantic Ocean, some from Europe, some from the east coast of the United States, to see if we can simulate like a cyclone. So let's go tape these down on the merry-go-round and we'll be back in a second.
So you can see my horrible cardboard representation of the US and Europe on the merry-go-round, and the X marks the simulated low pressure area over the Atlantic Ocean. Unfortunately, we didn't get a super clean take of this demonstration. It's surprisingly difficult to synchronize 3 people throwing simultaneously on a rotating platform. But anyway, we'll slow this way down to 10% of real time so you can see what's going on. As you can see, from the point of view of someone sitting on Earth in the northern hemisphere, these balls, which represent the air molecules, curve to the right as they move inward. If these were air molecules, eventually they would settle into this counterclockwise spin around the low pressure zone. And if you don't believe this is a real thing, here's a photo taken above Iceland by the Moderate Resolution Imaging Spectroradiometer, or MODIS instrument on board NASA's Aqua satellite. And it shows this large cyclone formed from the Coriolis effect. In our simplified example, the drone is playing the part of the geocentric NASA satellite because unless I get a ton more subscribers on my YouTube channel, all I can afford is this $500 drone, not a $952 million set.